Okay, here's the list. Let's go through the list first. Domain, X-intercepts, and multiplicities. 3, Y-intercept. 4, vertical asymptotes and behavior. 5, and behavior and horizontal asymptote. I will write in parentheses slant asymptote. 6, of course, max min. 7, symmetry. 'So one more time, domain, X-intercepts and their multiplicities, the Y-intercept, vertical asymptotes and behavior horizontal asymptotes, or asymptote, or slant. I'll explain. Max min, symmetry. 8. I'm missing something, and I'll get to it when I graph it. What am I missing? I just thought about mentioning one other thing. The range is not only if it's specified. Max min, symmetry. Number of turns is not valid here. We don't know that. The number of turns cannot be determined anyway for rational functions. I wanted to add one more thing here. It will come to me. Leave it open. Oh, yes, of course. The slant asymptote, if a function has, and I'll explain in a moment, if a function has a horizontal asymptote, it cannot have a slant. If it has a slant, it cannot have a horizontal. So that's why I put this in parentheses. So, and we'll see in a moment which functions have slant asymptotes and which functions have horizontal asymptote. Number 8, just skip my mind just for a second. When I was talking about this, I wanted to mention one other thing. I want to make a note before I forget. A function can cross, oh yes, a hole in the graph. Yes, sorry, I just remembered. A open point in the graph. Just came and left. So this is it, an open point in the graph. A function can cross a horizontal or slant asymptote, but never a vertical asymptote. Never a vertical asymptote. This is an important situation that I need to talk about. I don't want to forget. Okay. A function can cross a horizontal or a slant asymptote, but never a vertical asymptote. So this is our list. 8 steps. This is not always applicable. So basically there are only 7, but I need to talk about this and I don't want to forget. That's why I wanted to put in there. So you're not going to see this in your book. So you're going to see these in your book. But I want to put number 8 in there because this is a special situation that I don't want to forget. Okay, so we're coming back to our function, and this is our function, negative 2x plus 1. We know it's type 1, and I'll explain how it differs from type 2 and type 3. I have to start with the domain. What is the domain of this function? Or first of all, I will ask you what x cannot be, and then we'll figure out the domain. What is the value that x cannot ever take? Thank you. So obviously the domain is everything but negative 3/2. Any questions here? Why negative 3/2? Is it clear, everyone? Is it clear why? Yes? Okay, perfect. We're going to get the chart going. So I'm done with the domain. I'll come back to the rest. So I have negative infinity to 0, and to negative 3/2 and 0. And since there is nothing I can write under negative 3/2, I have to show that this is undefined. So far, from my list, I finished with the domain, and I got my chart going. Now the x-intercepts and their multiplicities. So the x-intercept is determined when? Good. When is a fraction 0?
Top 0.
Only when the top is 0. Negative 2x plus 1 equals 0. I move 1 and divide by negative 2, so x equals? I move 1 and make it, yes, very good. So 1/2 is right here, and I put it in the chart. I'm done with the x-intercept. What about its multiplicity? I have found one x-intercept. What is its multiplicity? This carries over from polynomials. Multiplicities carry over from polynomials. So what would be the multiplicity for this? 1, which means it's not going to be a turn, it's not going to be a cross flat, it's going to be a straight cross. Okay, perfect. So that is done too. Now I need the y-intercept. How do I determine the y-intercept? Good. So the y-intercept. So f of 0, here's what I do. How much is f of 0? Perfect. Perfect. I'm done with this. Okay. We have never seen this before. We have never graphed functions like the one that we are looking at this moment, with a point in which the function does not exist. We had a situation in which we had an open point, right? And the function may not exist there. We actually didn't. We had only piecewise defined functions where there was an open point and a full point somewhere else, right? On the same, for the same x value. So the function was always defined. So in this situation, the function does not exist at negative 3/2. And we will see that this line is a vertical asymptote at negative 3/2, and the function will either go to infinity or go to negative infinity, approaching that vertical line. This vertical line is called a vertical asymptote. The function will never cross it because it's undefined there. What happens on the other side? The same thing. The function could go to positive infinity or to negative infinity. In general, there are only few situations. Positive, positive, negative, negative infinity, positive infinity, negative infinity, and the other way around. So since this function is a rational function, undefined at negative 3/2, I know that x equals negative 3/2 is a vertical asymptote. I will make myself a note right here. x equals negative 3/2 is a VA. And in my mind, I jump to item 8. When will a function have an open point in the graph? Only if the denominator as a factor can be simplified with a factor from the top. Let me give you an example. So I make a parenthesis because this is very important. So let's suppose I have a function like this, f of x, x minus 1 over x minus 1 times x plus 2. What is the domain of this function? You cannot simplify before you write the domain. Yes, you could say, well, simplify these two and the domain will be anything but negative 2. I cannot do that. The domain has to be stated on the original function before I touch it. So obviously x cannot be 1 and x cannot be negative 2. So the domain will be negative infinity, negative 2, union negative 2 to 1, union 1 to infinity. We agree with that. In other words, not negative 2 and 1. Now, I can simplify these two. And the final simplified form of the function is x over x plus 2. Why am I saying all this? It's because x minus 1 disappears as a factor, so the function will have an open point in the graph. X equals 1 will not be a vertical asymptote. X equals negative 2 will be a vertical asymptote because that factor cannot go away. So this will create a vertical asymptote. This will only create a hole in the graph at 1. So I'm asking myself always, this item 8 always is on my mind, unless I have a senior moment and I forget. So what I was trying to say. So 2x plus 3 does not disappear as a factor. Therefore, x equals negative 3/2 is a vertical asymptote. So I'm done with this, but now I have to determine the behavior of the function near the vertical asymptote. Does it go to positive infinity or does it go to negative infinity? One or the other, not both. On the other side, does it go to positive infinity or does it go to negative infinity? One, not both. How do I do that? I pick a point very close to negative 3/2 from the left and from the right. Very close. I'm not going to put in the chart. I put it up here as negative 1.51 and negative 1.49. Negative 1.49 is in the immediate vicinity of negative 1.5 from the right, and negative 1.51 is the immediate vicinity of negative 1.5 from the left. All I have to do now is punch it in the function. Negative 2 times negative 1.49 will be a positive number, plus 1 will be a positive number. Negative 2 times this will not exceed 3. So the denominator is also positive. Would you agree? So 2 times negative 1.5 will be 3, but 2 times negative 1.49 will stay below 3. So this will be positive. Positive over positive, what will be the sign on the right-hand side of this asymptote? So I'm going to write positive infinity. On the left-hand side, this is still positive because it's negative 2 times negative 1.51 plus 1. But what happens to the denominator? Now 2 times negative 1.51 will exceed 3. What will be the sign in the denominator here? Negative. What will be the sign on the left-hand side of this asymptote? Negative infinity. So now I'm completely done with number 4. I found the vertical asymptote, and I found the behavior of the function near the asymptote. Okay. This function, I'm moving on to number 5. This function does not have a slant asymptote. The only function that has a slant asymptote is type 3, slant. No other function has a slant asymptote. So we are going to try to understand what the end behavior and the horizontal asymptote means. Or both. The end behavior we know, the horizontal asymptote. These functions, especially type 1 and type 2, these functions, rational functions, tend to approach a number. It's not always the case that they approach the same number to infinity and negative infinity. It's not. So some functions can approach positive 2 at one end and negative 2 at another. In this course, on both sides, they will approach the same number. But later on in calculus, you'll see we have functions that do this or do this. In chapter 4, we'll look at a function that does this. It only has a horizontal asymptote at one end, but it goes to infinity at the other. So that's possible as well. But this type 1 has a horizontal asymptote. How do I know? How do I know? Here's how I know. Bear with me for a moment. I have negative 2x plus 1 at the top and 2x plus 3 at the bottom. What is the degree again at the top?
1.
Good. I like to factor out x. What is the degree at the bottom? I would like to factor it out. If you had said degree 2, I would have factored out x squared. But you said degree 1, so I factored out x. Can you please give me what is left inside parentheses? So x times negative 2 is negative 2x. X times what is 1? True. Perfect. The second one, the denominator. 2 plus. Very good. Excellent. Okay, stay with me. One more step. Allow me to simplify x with x, and you can say no, because you didn't write x not equal 0. Correct. But I'm talking about what happens as x approaches infinity and as x approaches negative infinity. So allow me to say that I can get rid of that. So the simplified form, if you want, is negative 2 plus 1 over x and 2 plus 3 over x. Okay? Now, when x approaches a very big number, what will happen to 1 divided by that big number? So let's say I have this piece of paper, and I want to cut a little piece for everyone on the planet. And 10 years from now, I get to your door, and I knock on your door, and I say, I've been to India, to China, to South America, and I got to you. How much will you get from this piece? Because I divided this by billions of people. When I got to your door, what will be left for you? Right. So 1 divided by infinity is approaching 0. What about 3? I have 3 pieces of paper and I divide it for everyone. What will this approach? 0. What will the whole thing approach? Well, negative 2 over 2, which is negative 1. This is the horizontal asymptote. So this function, at infinities, it will approach negative 1. How? I don't know yet. It could approach from above and get closer and closer to negative 1. Or it could approach from below and get closer and closer to negative 1. I don't know. But I know for sure that the end behavior is negative 1, and y equals negative 1 is a horizontal asymptote. For type 1, we don't have to ever do this again. For type 1, it's always the leading coefficient divided by the leading coefficient. That is the horizontal asymptote and the end behavior. Done with this? I cannot determine that. This we talked about. And this, there is no symmetry. When a function has a vertical asymptote at negative 3/2 and does not have 1 on the other side, it cannot be symmetric. I'll say none. That's all we need. Ready for the graph now. When we graph functions with asymptotes, we must graph the asymptotes first. Mandatory. This function has two asymptotes. So I'm looking at the chart. Nothing else matters. I don't care about anything else. Just my chart. It will tell me what to do. So I have to graph a horizontal asymptote at -1. I have to graph a vertical asymptote at -1.5. And now I'm reading my chart after I plot the ordered pairs that I have. I have 0, 1/3, and I have 1/2, 0. I don't have anything else. So now, here's what my chart is telling me. From approaching -1, go down to -infinity on the left-hand side of the vertical asymptote. One more time. From approaching -1, go down to -infinity on the left-hand side of the asymptote. Okay, that's not a problem. It doesn't touch y equals x, y equals -1. So I'm done with the left-hand side. Now the right-hand side. From approaching +infinity to the right-hand side of the asymptote, cross the y-axis at 0, 1/3, cross the x-axis at 1/2, 0, and approach -1 from above of -1. No problem. So this is your function that you picked, -2x plus 1 over 2x plus 3. Now with the calculator, please make sure you put, bless you, top and bottom in parentheses. So in parentheses, we had -2x plus 1, close, divided by, in parentheses, 2x plus 3, close the parentheses. The graphing calculator will not graph, does not know to graph the horizontal asymptote. You have to put it in by hand. -1. The graphing calculator will not graph, in some cases, not even the vertical asymptote. I would use the standard viewing window. So I'm going to press on zoom and 6. Now let's see what happens. Here it's coming. It's coming. Yes. Yes. And the horizontal asymptote. It does not show the vertical asymptote at -3/2. -3/2 at -1.5. If you have an older calculator, it will show the vertical asymptote. So no secret, we followed our chart. We determined everything from left to right. We found the vertical asymptote, the horizontal asymptote, the end behavior, x and y intercepts, and that's it. Now I'll stop. Yes, I'll stop. The second type, the only difference is that it has 0 here. Because the denominator is so much bigger than the numerator, like we had 1 over x, it went to 0. And the third one has a slant asymptote and not horizontal. And that will be the end of chapter 3. So on Wednesday, I'd like to finish up this and review for the test. And hopefully we can have the test on Monday. If you want it on Wednesday, I'm fine with that too, but I have to continue.